So bonding and structure, in the last session, we started with ionic bonding, the bond which is formed by a complete transfer of electron between the metal and the non-metal. Metal tend to lose electron where non-metal tend to gain electron, and the electrostatic attraction between the ions is known as the metallic bond. And these ions, they arrange themselves in a regular pattern or structure which we call a lattice. And when these ions in a gaseous state come close to each other from a compound, we call that as a lattice energy. The ionic radii, the positive ions have a smaller ionic radii or smaller radii as compared to the atom because it has one less shell electron, or the ratio of the proton and electron increases, so greater net force on each electron. That's why the size decreases. Whereas for negative ions, when we compare the size of the negative ions, as they gain electron, formation of a negative ion is by gaining electron. So they have more electron than corresponding number of the proton. So the pull of the nucleus over more electron, each electron decreases. That's why the size will be larger. So when we compare these isoelectronic structures, nitrogen is having 10 electron, oxygen ion is having 10, fluoride ion 10, neon atom 10, sodium ion 10, magnesium ion 10, and aluminum also 10. But the number of the protons are different. For nitrogen, there are 7 protons, 8 protons, 9 protons, and sodium 11 protons are there, 12 proton and 13 protons. So you can see the proton to electron ratio is higher, so more protons, greater attraction. That's why the aluminum size is so small compared to other isoelectronic structures. Same way for nitrogen, there are 10 protons, but there are 10 electrons, but only 7 protons are attracting. So the net size of this nitrogen ion will be higher because the size depends on the ratio of, if protons are more, size will be smaller. If electrons are more, size will be bigger or larger compared to a neutral atom. Then these are certain definitions which you have to learn. The definition which are involved in enthalpy change. Number one is the formation. What is the meaning of formation? When element in their standard form gives a compound, we call that as a formation energy. Atomization means when we produce atoms in the gaseous state, we call atomization energy. So sodium is there, but atom in solid state. So when we atomize, we produce sodium atom in a gaseous state, we call that as atomization. Same way, because if we have one oxygen molecule, this will result in a formation of two oxygen atoms. So that will be twice the atomization energy. If we want for single atom, so if we have half molecule of oxygen, it will give one atom. We call that as atomization. This is just a quick revision what we have discussed last week. Then first ionization and the second ionization. The term ionization means energy required to remove electron. So when we remove first electron, we call that as the first ionization. When the second electron is removed, we call that as the second ionization. But again, the condition, it should be in the gaseous state. First electron affinity and second electron affinity. So first electron affinity, it is energy released when electron is added to a neutral atom, and second electron affinity when electron is added to already a charged ion. So first electron affinity is always exothermic, but the second electron affinities, second, third, fourth, they all are endothermic. What is the reason for that? Because already there is a negative charge on the sign, and electron is also negative, and like charges repel each other. So as the like charges are repelling each other, we have to supply energy so that the electron can be added or come closer to this negative ion. But in this case, there was a neutral atom, electron is added to a neutral atom, that's why it is exothermic, the react bond formation is there and it happened by itself. So first electron affinity is always exo, second, third, fourth, fifth, they are always endo. And the lattice formation or lattice energy, when ions in the gaseous state form a compound, they release energy. We call that as a lattice energy. And this lattice energy depends on the size of the ion. So size of the ion should be small as possible, and the charge on the ion should be large as possible. So that highest lattice energy for small size and greater charge. And why there's a difference between theoretical and the Born-Haber values? Because theoretically we consider ions are perfect spheres, but practically it does not happen. That there's a distortion of polarization is there for the negative ion, and due to this distortion the lattice energy increases as ions come much closer to each other. So Born-Haber or experimental values are always higher as compared to theoretical. If theoretical and Born-Haber have the same value, we say that the bonds are 100% ionic, or the charges are perfect spheres. And this distortion depends on the size of the positive ion. It should be small, charge of the positive ion should be large, and the size of the negative ion should also be large. So the one which will have a greater difference in the theoretical and the experimental lattice energy, it means that is having the greater distortion. Then the properties of ionic, they have high melting point, does not conduct in solid because ions are not free to move but can conduct in molten or aqueous. And they are brittle, means when you apply a force, they break down with a certain force without showing a deformation, so we call them as brittle. So this was all about ionic, and this is the experimental confirmation that ions are present. When we do electrolysis, we are able to observe the movement of the charged ion, which confirm that ions are free to move in the electrolyte, or the existence of the ions. Today's topic is about the covalent bond. What is a covalent bond? A bond which is formed by sharing of electrons. So when atoms share electrons such as group 4, 5, 6 or 7, or the non-metals we can also say, which include, we have group 4 is there. So group 4, because they tend to complete octet, so they will have 4 electron in the outermost shell. So to complete the octet, they will share So group 4, it will share 4 electrons, and as it share 4 electron, how many unshared will be there? So the unshared will be 0, because 4 electron in the outermost shell, all 4 are involved in the sharing. For group 5, the group 5, they will share 3 electrons, and unshared will be 2. So out of 5 share 3, and because to complete octet, they have already 5 electrons, so they will share 3 to complete octet. For group 6, they will share 2 electrons, and the unshared will be 4. So 6 electrons are already there. Out of 6, they will use 2 in sharing, and remaining 4 unshared will be there. So the total sum will be 8. And group 7, it will share only 1 electron, and unshared will be 6 electrons. So about group 8, because it is already having a complete shell, so group 8 does not tend to share the electrons. Now, what is the experimental evidence that there is a covalent bond or there is a sharing of electron between the atoms? So when we carry out X-ray diffraction of hydrogen, X-ray diffraction means like we have hydrogen gas. So what we are doing, we are passing X-ray through a sample of hydrogen molecule. So the X-ray diffraction of a hydrogen shows that a high concentration of negative charge between the nuclei. So what it shows that there is a greater density of electron or high density of electron between the two nuclei. And this charge is strongly attracted by both nuclei, so the attraction exceeds the repulsion. Because what happened, basically, when we compare the structure of a hydrogen is having one proton inside the nucleus, and there is one electron. Same way for other hydrogen, there is one proton inside the nucleus, and there is one electron, and there is a sharing of electron between the two. So when we pass X-ray, what pattern we observe? We observe that greater electron density is there, or greater number or probability of finding electron is maximum between the two nuclei. So what this region shows that maximum probability or maximum chance of finding electron is there. So even though like charges are repelling each other, as you can see, the negative charge is strongly attracted by both nuclei. So they are attracting this negative charge, even though there is a repulsion between the like charges, like negative and negative, or electron electron, but that is attracted towards the nuclei, and that attraction exceeds the repulsion. So there is a bond or attraction which we call a covalent bond. So in a covalent compound, there is a significant electron density between the atom. What is the meaning of electron density? Electron density means the probability or chance of finding electron is maximum. So when we have greater chance or higher electron density, so simply the electron density means number of electrons per unit volume. So higher electron density means greater chance is there of finding electron. So when we do or carry out the X-ray diffraction, this type of pattern we observe for covalent substances. But if same X-ray diffraction is done for ionic compounds, so what we observe, there's a different pattern for ionic compounds. For ionic compound, we see separate electron density for positive and negative ions. This is the electron density map for ionic compounds, which shows that there are ions present, but they are not actually overlapping with each other. Still, there is gap between them. But what about the covalent substances? The electron density map of the covalent substance, what it appear? It appear the maximum probability or chance is there for finding electron is maximum between the two nuclei. Like example, this is one nuclei, this is another. So we find maximum probability or chance is there of finding electron within this region. Is it clear the difference of electron density for covalent molecules and ionic compounds? Any doubt in this part? So for covalent substances, only single line around both nuclei. But for ionic compounds, there are separate contours or there are separate lines to explain each ion. So how to draw the covalent structure? Drawing the covalent structure. If I say we want to draw the structure of ammonia, which is NH3, so we'll check the group. Nitrogen, it belongs to group 5. So as it belongs to group 5, it will share 3 electrons. And there will be unshared 2 electrons. About hydrogen, it will have 1 electron only, it share 1, and unshared will be 0. So we have one nitrogen and three hydrogen. The one which share the maximum number, you should draw at the center. So nitrogen should be there at the center and surrounded by hydrogen. When you start sharing, you will start sharing with the one which share the least number. So hydrogen is there. So if hydrogen share one, from that side nitrogen can share one only. Same thing, hydrogen share one, from that side nitrogen share one. Hydrogen share one, from that side nitrogen share one. And there are two unshared electrons on nitrogen. So when we complete this structure, hydrogen ring of a hydrogen, like for hydrogen atom, maximum 2 it can adjust as it's only one shell, and for nitrogen maximum 8 it can adjust. So this is a covalent bond between nitrogen and hydrogen when one nitrogen bonded with three hydrogen atoms. Then one more thing, you have to identify how many bond pairs are there, because that is important to predict the geometry of the molecule that we'll discuss later in this session. So how many bond pairs are there? The total number of electrons. So there are three bond pairs. So the total number of pairs, so total number of electron pair, that is equals to 6. Sorry, 8. Sorry, by mistake, it's 4. I was counting the number of electron. It's pair. Then when we check the bond pair, number of the bond pair, that's 1, 2, and 3. So 3 bond pairs are there. And how many lone pairs are there? The number of the lone pair when you check, so that is equals to 1 only. Why it is important to identify the number of the bond pair and lone pair? Because you should be able to predict the geometry of the molecule as well as the bond angles. So this table is very important. You have to basically learn this table. If you find that two bond pairs are there and there is no lone pair, then the bond angle, this bond angle will be 180 degrees, and that structure is known as a linear structure. We will do example for each. If there are three bond pairs and there is no lone pair, then bond angle will be 120 degrees, and that structure is known as trigonal planar. If there are four bond pairs and there is no single lone pair, then the bond angle is 109.5. You have to learn these angle, and the geometry will be tetrahedral. If there are three bond pair and one lone pair, so three bond pair and one lone pair, this is the same example which we did just now. So what will be the structure? That's called trigonal pyramidal with a bond angle of 107. If there are two bond pair and two lone pair, then the bond angle will be 104.5, and the structure is known as a bent, or you can also say V shape. If there are five bond pair and there is no lone pair, then it will be called as a trigonal bipyramidal with a bond angle of 120 and 90. So this is 90 and this angle is 120. If there are six bond pair and there is no lone pair, so each bond angle will be 90 degree. These dash and wedge, what they are representing? They are representing in and out. Like one of the bond is into the plane, another one is out of the plane. So this table is important. I will give example. Like normally you will find a question after drawing the structure. They ask how many bond pairs are there, how many lone pairs, and then predict the geometry. But what you observe, you can see if there are four bond pairs, the bond angle is 109. But if three bond pair and one lone pair, the bond angle is 107. So how much is a change? That is 2.5 degrees. Same way, if we have two bond pair and two lone pairs, so lone pair increases. So how much is a change? 107 minus 2.5, so that will be 104.5. So due to the presence of each lone pair, the angle will decrease or change by 2.5. And what is the reason for that? So there is a theory which explains the geometry of the molecules, and that is known as valence shell electron pair repulsion theory. So the valence shell electron pair repulsion theory is the reason why different bond pairs and lone pairs, like different number of bond pair and lone pair, leads to a different geometry. What is this theory? It states that the repulsion between, because electron pairs they will repel, the repulsion between lone pair and lone pair is greater than or more than the lone pair and bond pair, and that is greater than the bond pair and bond pair. So this is called valence shell electron pair repulsion theory, that lone pair have more repulsion than lone pair bond pair, and they will have more repulsion than bond pair and bond pair. So what is the effect of increasing repulsion? If they will have more repulsion, the bond angle will decrease. So as you can see, when we compare, like example, this part, because when we are comparing, one of the parameters should be same, so total number of pairs should be same. The total number of pair, that is 4, this is 3 and 4, and this one is also 4. But when you compare, there are 4 bond pair, there is no lone pair, so they all are bond pair. This is having a bond pair and lone pair, but this is having bond pair and 2 lone pairs. So this, which will have the maximum repulsion? This will have the maximum repulsion. As it will have a maximum repulsion, the bond angle, when we are comparing this, so this will have the smallest bond angle. Because why we are not comparing this with other like octahedral? As we know, the total number of electron pair should be 4 for a fair comparison. The total number of electron pair should be same, and then we'll check the number of the bond pair and the lone pair. So the one which is having the highest number of the lone pair will have the maximum repulsion, and maximum repulsion leads to a smaller bond angle. Here there are 4 bond pairs, there is no lone pair, so this will have the minimum repulsion in these 3, and as it will have the minimum repulsion, so it will have the maximum bond angle. Is it clear, the comparison, that why as the number of the lone pair, because lone pairs are relatively free, they can move easily, that's why they have greater repulsion to the other electron pairs, which leads to a bend in a geometry or the structure. So when we are drawing this structure, you should always check the number of the bond pair and the number of lone pair. Example, if I say we have a compound OCl2. So first we have to draw the structure. We know oxygen, it belongs to group 6, that will share 2 electrons, and the unshared will be 4. Then chlorine is there, it belongs to group 7, it will share 1 electron, and unshared will be 6. So we draw oxygen first, and that is surrounded by chlorine. So each chlorine share 1, oxygen share 1 from that side, chlorine share 1, oxygen share 1, and there will be 2 unshared on oxygen, 4 unshared on oxygen, and 6 unshared on chlorine. So when we predict the geometry, predict the shape, we always predict from the central atom. So we don't check all the atoms, even though chlorine is also having lone pairs, 6 lone pair. But when we check or predict the geometry, we always check the central atom. So the central atom in this example is oxygen. And when we check oxygen, the total number of electron, how many bond pairs are there? So there are 1 and 2 bond pairs. And how many lone pairs are there? There are 2 lone pairs. So oxygen is having 2 bond pairs and 2 lone pairs. So a molecule with 2 bond pairs and 2 lone pairs. So 2 bond pairs are there as well as 2 lone pairs. So what should be the geometry? It will be a bend of V shape with a bond angle of 104.5. So when we draw the structure, this is we represent the sharing, but how it will be, how the structure will appear. So there will be oxygen having 2 lone pairs, which will have maximum repulsion, so greater gap between the lone pair, and that they repel the bond pairs. We'll have chlorine, and this bond angle will be 104.5 degrees. It appeared to be less than 104, but it should be, because of space I did not extend the angle, but it should be 104.5 degrees. Is it clear, this idea of predicting the geometry or the shape of the molecule? Sometime you have a molecule which is having, like if I say we have CH3, CH2, OH, and they ask predict the bond angle of H, C and O. So when they say HCO, C is the central atom. Now what will be the geometry first? Carbon belongs to group 4, so it will share 4 electron. Oxygen belongs to group 6, so it will share 2 electrons, and hydrogen having only 1 electron. Here we'll have hydrogen, hydrogen, hydrogen. So we have to predict the bond angle or the geometry for HCO. So what is HCO? You can take this HCNO, or you can take up one. So which is a central atom? Carbon is a central atom. So when we are predicting the geometry now, we should check the carbon. So when we check this carbon, the central atom is carbon. How many bond pairs are there? 1, 2, 3 and 4. There is no lone pair. So the total number of the bond pairs are 4, and total number of lone pairs 0. So 4 bond pair and there is no lone pair. So what is the geometry of this molecule when 4 bond pairs are there and there is no lone pair? So it will be a tetrahedral with a bond angle of 109.5. So we'll mention it will be tetrahedral with a bond angle of 109.5. But what about the same question was there, and they asked predict the bond angle for COH. So COH is this part. Now the central atom is oxygen. So you have to predict, check oxygen. When you check oxygen, the number of the bond pairs are 2 and number of the lone pairs are 2 as well. So 2 bond pair, 2 lone pair, it will be a bend or a V shape with a bond angle of 104 degrees. Is it clear? So it depends on, if you have a long chain molecule, then it depends on the question which structure, which part of the chain they want the bond angle, as it vary from molecule from one part of the chain to another. Is it clear, this example? Then before the metallic, there's another type of a bonding which we call dative bonding, or it is also known as coordinate covalent bond. What is the meaning of dative bond or coordinate covalent bond? It's also a sharing of electron. So but in this case, both electrons are coming from same atom. So both electrons are actually a sharing of electrons, but both electrons are coming from same atom. We call that as dative bond. Example, so we have ammonia in which nitrogen is forming a bond with hydrogen and there is a covalent bond. And nitrogen is having a lone pair. So all of the atoms which are there in the structure are stable. But what happened? Example, if there is a proton in the atmosphere, means in the region. So proton, H plus sign or proton, it means that is only one proton. It does not have any electron, no electron. So this proton adjusts with a lone pair of nitrogen. So when it adjusts with a lone pair of this nitrogen, so as you can see, both of the electron belongs to nitrogen. Hydrogen does not share any electron, but it appeared to be a sharing of electron. So what we call this bond, the bond, it's also a sharing of electron, but that is due to the one atom only. And the molecule will get a charge. Why a molecule will get a positive charge? Because NH3 was neutral, but there is hydrogen present which is having only proton. That's why the net charge on the molecule will be positive. So three of the bonds are covalent and one of the bond is a dative covalent or coordinate covalent bond. So when electron, a pair of electron which is shared between the atom, both electron belongs to same atom, we call that as a dative bond. And how we represent, how to distinguish? So example, we have nitrogen sharing electron with hydrogen, and there is a dative bond with another hydrogen, extra hydrogen. So we draw an arrow. The element which is sharing both of this electron, we draw arrow from that element to the one which is taking those. But still it is a sharing. It's not like the two electron transfer from nitrogen, and this will get a net charge of +1 or positive. So we call this as a ammonium ion. Is it clear? The dative bond. And what about predicting the geometry? There is a same way to predict the geometry. First, when we are predicting a geometry, first we were having NH3. And now we have NH4 ammonium. So predicting the geometry depends on the bond pair. So for ammonia NH3, and for ammonium, which is NH4. So when we check the bond pairs, there are 3 bond pairs, and when we check the lone pairs, there is only 1 lone pair. So 3 bond pair and 1 lone pair. What will be the geometry for 3 bond pair and 1 lone pair? So it will be trigonal pyramidal. So what is the geometry of ammonia NH3? That is trigonal pyramidal with a bond angle of 107 degree or 107.5. But what about NH4? So we consider this as a bond pair now. So all 4 bond pairs are there. There is no lone pair. So there are 4 bond pairs and there is 0 lone pair. So 4 bond pair, no lone pair. What will be the geometry? It will be tetrahedral with a bond angle of 109. So as you can see, when it is tetrahedral 109.5, that was 107. So this was 107 and this is 109.5 degrees. Is it clear that as the number of the bond pair changes, the geometry of the molecule also changed?